Today's topic is the meter bridge. Now, meter bridge is an application of Wheatstone bridge or Wheatstone bridge principle to. So it's actually really an application of Wheatstone bridge. So it's also called as application of Wheatstone bridge to meter bridge. So the topic so explain an application of Wheatstone bridge to meter bridge like that, or explain application of Wheatstone bridge principle to meter bridge. That way also the question can be given. So really, a meter bridge is the practical form of the Wheatstone bridge. So Wheatstone bridge, already we have seen that it is very useful to determine any unknown resistance or to compare two unknown resistances. So how really an unknown resistance can be determined using Wheatstone bridge means, so practically a Wheatstone bridge can be constructed. So the most useful form of the or practical form of the Wheatstone bridge is the meter bridge. Now why it is called as meter bridge? The Wheatstone bridge, when it's constructed such that it's practically useful, then it is called as meter bridge. What is the reason? Now, the reason for this can be understood from the simple diagram of the regular Wheatstone bridge. So in the Wheatstone bridge already we have seen that there are four resistances P, Q, R and S. So in between a galvanometer is also there. But the important thing is the balancing condition is expressed in terms of these four resistances P, Q, R and S. Now of these four resistances, the top left and right are P and Q, and the bottom left and right are R and S. Now these two resistances, the bottom left and right resistances R and S, they are actually formed by a single 1 meter long uniform resistance wire. 1 meter long uniform resistance wire. So the Wheatstone bridge, when it's constructed practically, how it is constructed practically, this already we have seen in the Wheatstone bridge itself. So there at one point we have seen this particular important thing. So the main thing there is the two lower resistances, that is the bottom left or the lower left and lower right resistances R and S, they are constructed from a single uniform wire, resistance wire of exactly 1 meter length. So that's nothing but a Wheatstone bridge in which the bottom resistances are formed by 1 meter length wire. That's why this Wheatstone bridge is called as a meter bridge. So that's the real practical form of the Wheatstone bridge, which is simply called as the meter bridge here. Now this is very important question again from the board examination point of view. So it carries again mainly 8 marks question, 8 marks to 5 marks. So there's not much place here. So I'll just do one thing. I'll just move this a little down, so the marks can be written easily, the weightage can be seen clearly. So this way I'm just moving it, so now this is much more clear. So this is very important topic, as important as the Wheatstone bridge. So always in the board exam, almost every year, either Wheatstone bridge is asked or the meter bridge is asked. So the regular theoretical Wheatstone bridge is asked, or the practical form of Wheatstone bridge, which is nothing but the meter bridge is asked. So it's very useful for 8 marks as well as 5 marks. That's a question. Just like the Wheatstone bridge. Now, what is the how the meter bridge is actually constructed? So that it's really a practical form of Wheatstone bridge. What is the construction? The construction can be understood directly from this diagram. So I've drawn the diagram before itself, so to save time. So it's very simple to draw the diagram. So just see here. Once the construction is understood, diagram drawing also will be very easily understood. Now, actually, it consists of a 1 meter long, slightly more than 1 meter length wooden board. Wooden board means it looks like this, a rectangular wooden board like this. It will be looking like. So on this rectangle, so I'm just drawing this roughly, the diagram. So this is a real diagram. So this 1 meter long wooden board, on this two L-shaped metal strips are actually fixed like this. This is one L-shaped metal strip like this, and this is the other L-shaped metal strip this way. They are fixed. So distance between them is about 1 meter. So the distance between the wooden board is slightly more than 1 meter, but the distance between the two L-shaped metal strips is exactly 1 meter. Now the first L-shaped metal strip is denoted as M, and the second L-shaped metal strip is denoted as N. That is what is shown here. So this I have drawn roughly. So the only thing is in the diagram the wooden board is actually not shown, because the diagram already too many details are there in the diagram, especially the four resistances are important, P, Q, R and S. So the symbols of P, Q, R and S are slightly changed. This is a real Wheatstone bridge. P, Q, R, top, left and right, P and Q. and the bottom left and right R and S. So these four resistances, galvanometer and other things are also shown. So too many things components are present in the which meter bridge here. That's why the wooden board is actually skipped off. It's not at all shown here. It's just understood. So directly in they cannot be the wire, different four resistances wire, galvanometer, everything can't be directly placed on a say in empty air or on the floor or on a table. So to have a fixed arrangement, so what is done is compulsory wooden board has to be used so that everything is fixed onto the wooden board. So that's understood. So wooden board is actually skipped off in the diagram. So I'm just removing this here, the wooden board and the other things. So diagram and also the page also looks very simple then. So this is coming back here. So on the wooden board, the two L-shaped metal strips M and N are actually fixed, firmly fixed. Now both these metal strips are actually made up of brass or copper. They are thick strips, metal strips, rectangular strips actually. Each this is one rectangular strip, this is another rectangular strip, welded actually strongly. Or a single strip, exactly L-shaped also it can be directly prepared. So it's very thick, it has sufficient thickness due to which what happens is the resistance will be, so when the area of cross section of any conductor increases, we have seen that resistance is decreasing. So already copper or brass have very low resistance, almost zero resistance. So now the resistance will be almost exactly zero because of the thickness or the more area of cross section. So that's very important here in the meter bridge construction. So the L-shaped metal strip M has almost exactly zero resistance. Even the L and the other L-shaped metal strip N also has an almost exactly zero resistance. Now between these two metal strips, L-shaped metal strips M and N, another straight metal strip is actually arranged. Now this straight metal strip is denoted as B here. The letters are also very important because Wheatstone bridge, just observe here, Wheatstone bridge network, the four resistances PQ, R and S are actually they are forming almost like a square loop or a roughly a square loop. So this square loop is denoted as what? A B C D A. A B C D A. So that lettering is very important here. So that lettering is actually maintained in the meter bridge here. So the lettering here, it's noted as the actual circuit network excluding the galvanometer, ignoring the galvanometer, is actually noted as ABCDA, the closed loop, which is actually formed by the four resistances PQ, R and S that were already seen in the Wheatstone bridge. So the same lettering is actually maintained here in the meter bridge. That's the important thing here. So the metal strip B is actually fixed onto the same wooden board in between the two L-shaped metal strips M and N. Now once the metal strip, so B also it's made up of the same material, brass or copper. Again it has the same thickness, so its resistance also will be zero. Now that's very important here for the working of the meter bridge. Now once the metal strip B is placed here two gaps are found. One left gap is actually formed and the right gap is actually formed between the left metal strip and the straight strip B. A gap is formed. That's called as left gap of the meter bridge. And similarly, again between the straight strip B and the L-shaped strip N, another gap is formed. Now in these two gaps, actually resistance are actually connected. In the left gap, an unknown resistance is actually connected. X it's denoted as, which is actually to be determined using the Wheatstone bridge principle. And in the right gap, a known resistance is connected in the form of a resistance box. Now, what is a resistance box? A resistance box consists of different resistances, known resistances, like 5 ohms, 10 ohms, 100 ohms, 200 ohms, 500 ohms, like that, 1000 ohms, 10,000 ohms, like the different resistances. Any one resistance can be used at a time. So any known resistance can be used here in the resistance box because different types, different values of resistances will be actually arranged in the resistance box. Any one resistance at a time can be used. So that known resistance value is denoted as RB. So resistance box short form is what? Abbreviation RB, capital RB. That's what is shown here. And its symbol mathematically also it's taken as capital R and small b. Again it stands for the same resistance box. Now that's the thing. Now between the two metal strips, the distance between the metal strips is exactly 1 meter length. So a 1 meter long uniform resistance wire is taken, which is made up of say manganese or constant N, any resistance such. So usually manganese and constant N are have high value of resistance or specific resistance. So they are the best materials which are actually used as the resistances. So such a material resistance wire is actually which is actually of uniform cross section and exactly 1 meter length, is actually arranged, connected between the left metal strip M and N. So that resistance wire, 1 meter long resistance wire, is simply known as AC. It is simply known as AC. So that's the next thing. Now between the metal strip B and a jockey J. Now what is a jockey J? So it's actually shown as an arrow here. Jockey J is actually shown in the diagram as an arrow here. Just it should be remembered. Now what is the jockey J? So jockey J here is nothing but a metal rod, just a metal rod, again made up of the same material, brass or copper. So again it has zero resistance. Now the purpose of this metal rod is, so actually a metal rod, it has two ends. So one top end, imagine that the metal rod is vertical like this, the top end and the bottom end. So here actually the top end and the brass strip B, in between the brass strip B and the top end of the metal rod, a galvanometer is actually connected. So bottom end is free. Now the purpose of the bottom end is, so the metal rod actually looks like this, somewhat like this way. It's a very simple thing like this way. Now the bottom end has a knife edge, its edge will be sharper. So this bottom end is actually placed, pressed onto the wire AC, the long resistance wire. This resistance wire is called as the bridge wire, the meter bridge wire it's called as. Now this is what is very important. Already I said before, even in the Wheatstone bridge also I said, the bottom lower resistances, bottom left R resistance R and the bottom right resistance S, they are actually formed by a single resistance wire of 1 meter length. In the meaning definition of meter bridge we have seen, that is nothing but the resistance wire AC itself. So this is simply called as the bridge wire or the meter bridge wire or meter bridge resistance wire. So now jockey J is actually brought into contact. It's pressed at any point. The point of pressing is very important in the working of the meter bridge. That point at which the jockey J is brought into contact on the bridge wire AC, that point of contact is called as D. This point D is very important. Why we'll be seeing in the next step itself. So between the jockey J, so this is a wire actually going from the top of the jockey. The bottom end is actually sharp, knife edge. It's almost like a knife edge. So that is actually shown by as an arrow here. So between the jockey J and the straight metal strip B, a galvanometer is connected by using connecting wires this way. That's the thing. So now when the jockey is brought into contact at any point D, then what happens is this entire meter bridge exactly behaves like a Wheatstone bridge. Exactly will be identical to a Wheatstone bridge. And another small thing here is between the ends A and C, a plug key K, just an ordinary plug key. Just an ordinary switch. By closing this metal strip again, by pressing this downwards, the circuit gets closed. If it is left again, it will be almost like a spring, like it will be working like a spring. It will go up again, and circuit gets disconnected. So they simply called as, really it's called as a key, but the word key is actually usually not used. It's plug key it's used. So plug key and the pressing key are almost similar. Slight difference will be there. In the lab, in the physics lab, you'll be seeing what is the exact difference. Roughly they can be taken to be almost same. So now a plug key K and a battery of EMF E are now connected in series between the ends A and C of the bridge wire. Now this forms an exact Wheatstone bridge. Now how this forms an exact Wheatstone bridge? This can be understood clearly like this. Now imagine that the plug key is closed. Once the plug key is closed, immediately current starts flowing. Now I'll use a different color, say an yellow color. So this way, the battery always sends current which is directed from the positive terminal. It goes into the network of all these resistances and again comes back to the negative terminal. So this current actually which is flowing, I'll just show it this way. It will be directed towards this way from positive terminal, away from the positive terminal, it will go into the junction A, it will be going. At the junction A, it divides into two parts. One part goes through the metal strip M and it goes through the unknown resistance X. That way it will be going. And the other part goes through the bridge wire from A to D and D to C, like that it will be going. So now the important thing is when the current is flowing through the metal strip, the resistance of the metal strip already we have seen that it is 0. If resistance is 0, then you take any 2 points. So you take the point A and this point where the actual resistance, left end of the resistance wire X, resistance, unknown resistance X is actually connected. Between the point A and this particular point, the other end of the metal strip, this is the other end of the metal strip roughly. So between this end of the metal strip and this end of the metal strip, the resistance is completely zero. When the resistance is zero, what is the potential difference? Potential difference across any resistance is given by current into resistance. So for example, we want a potential difference. Supposing you take a resistance like this. So we'll just take a resistance like this simply, this way. When current is flowing, so across this two ends of the resistance, call these 2 points as the two ends of the resistance. This resistance. Resistance means it's a resistor. It's a conductor having some resistance. So supposing the resistance value is R, current is I. Product of current and resistance is what? Potential difference between the two ends of the resistor. That's how we are finding out. But now the metal strip is having how much resistance? Again, I'll use the same color, regular blue color. So with yellow is actually not visible. So you are most probably seeing the video on a phone. So yellow will be very difficult to see on the phone. So only so certain things, for example, instead of using a pencil will be very light when you are writing on paper in the notebook. You are using pencil along with pencil will be very light, almost like similarly I'm using this, so that it will not be actually affecting the main figure, main diagram. So now what is happening here is when current is flowing to the metal strip, the potential difference across the two ends of the metal strip is exactly zero. The reason is potential difference is current into resistance. Resistance being zero, so potential difference will be zero. Potential difference is nothing but difference of potentials. So at this end potential is, we call it as A, VA, because this is end A, VA. So this end I'll call it as same V X. I'll call just Vx. Actually X is different, this is the resistance, but because there is no alphabet here, I'll just take it as, or I'll call the end A as V1 potential. The other end of the metal strip I'll call it as V2. So what is the potential difference? That potential difference is simply what? V1 minus V2. That is coming as 0. That means V1 minus V2 is 0, means V1 is equal to V2. That means both these points are at the same potential. Not only these 2 points, you take any other point here also, again in this also, in this part also potential difference is 0, because resistance being 0. So this point is again potential is equal to VA. That means all the points on this metal strip are at the same potential. Due to this reason, this entire metal strip will act as a single point with a fixed potential. That's important. That's the reason why the metal strip is taken to be of zero resistance. So this will act as a single point with a single point potential, single potential. So this simply means that the left end of the unknown resistance X is, it's as if directly it's connected to the end A, such that left end X of the unknown resistance and the end A are at the same potential. It's as if the left end is directly connected here. Then what will be the diagram here? It's very simple. So the left end I'm just taking here, see unknown resistance X. The left end is actually here, I'm taking it as the lower end. It's directly connected to the end A itself. That's way. So metal strip can be completely ignored. So now you take the right end now. Right end is connected to strip B. Again strip B has zero resistance. That means the potential difference across the two ends of the strip B is again 0. That means this left end and right end are at same potential. So not only this, all the points on the strip B are at the same potential. So it's almost like a single point. So the entire metal strip will act as a single point with a single potential. Now this simply means that both the right end of the unknown resistance, it's as if it's connected directly to the left end of the known resistance RB at a single point, like that. So the right end here in the in this diagram, I'm just showing the right end as top end. It's almost right only, but slightly for convenience I have drawn it a little upwards inclined. I have drawn, that's the only difference. The right end is directly connected to the left end of RB. So left end of RB also I'm writing inclined, because this diagram is almost similar to, I said it's all, not almost, it's identical to the diagram of the Wheatstone bridge, in which we are showing the resistances in inclined manner. So that diagram is much more. So we can draw this square as a rectangle also, like this also we can draw this ABCD. But that's actually much more complicated. So this is much more simpler representation of the Wheatstone bridge. So anyway, it can be drawn. Some textbooks don't draw it like this. They draw it as a regular rectangle like this. They'll be drawing. So that way also, that's also okay. But we are following this. It's better to follow the same thing. So now same diagram. So now the left end of the unknown resistance X is direct. It's as if it's directly connected to the right end. That is the right end of the unknown resistance X is as if it's directly connected to the left end of the known resistance RB. So the right end of unknown resistance X, this is the right end. It's directly connected to the left end of the known resistance RB, that way. This way it's connected. So now again, so whatever things we are seeing here are simple, nowhere any complication is there. So now what about the right end of the known resistance RB? Again, it's connected to the left end of the L-shaped strip. And the right end of the L-shaped strip is what? The other end of the L-shaped metal strip N is here. Now again, this is also, this metal strip N is also of zero resistance. So all these points will be at the same potential. Observe the cursor compulsorily. Now all these points on the second L-shaped strip N can be read again as a single point with a single potential. So it's as if the right end RB is directly connected to the end C. So it's directly connected to the end C of the bridge wire AC. Now this bridge wire AC, once the jockey is pressed at point D, we can imagine that the bridge wire consists of two parts. One is the resistance AD and the other is the entire resistance of the bridge wire. It's of 100 centimeters length. So AD is actually a part of the total length AC, which is equal to 100 centimeters. 1 meter means 100 centimeters. So actually it's much more easier to express the length 1 meter in centimeters, so that we can take it as a simpler number 100 centimeters. So 1 meter, again if we take less than 1 meter means decimal fraction it comes. So to avoid decimal fraction, it's better to measure the length, total length of the bridge wire 1 meter length as 100 centimeters. So then this part AD will be less than 100 centimeters, something like 40 or 50, and this part DC will be the remaining length of the 100 centimeters. So that way. So once the jockey is brought into contact at the point D, now this AD will behave as one separate resistance. AD I am drawing it here. So actually AC should be drawn here. I'll just draw this, divide this into two portions. One is AD this way and the other resistance is DC. So that is DC this way. Now just observe here. This resistance between A and D, it can be called as RAD. Between A and D, this resistance can be called as what? Simply RAD it can be called as. And this resistance between D and C can be called as RDC. So this is RAD and this is between D and C is what? RDC this way. Now just see here between B and D. So this is what? A. So end A is directly, it's as if connected to the left hand X of the unknown resistance X. So this way, and the right end of the unknown resistance X is directly connected to the left end of the known resistance RB at S. It's almost like a single point. The entire metal strip can be read as a single point B, so I'm just calling it as B. So now between B and D, D is the point of contact of the jockey. Already we have seen that between B and the jockey J, a galvanometer is connected. Jockey J is nothing but its position is the D itself. It's known as D in the diagram on the resistance wire, bridge wire AC. So a galvanometer is connected between B and D. So between B and D, a galvanometer is connected. Now again between A and C, a plug key and a battery. Between ends A and C, a plug key and a battery are connected this way between the two ends A and C. Now just see here, this is the battery, this is the plug key. Now how is this Wheatstone meter bridge? See, it is same as the Wheatstone bridge. Let's see here, this is the same Wheatstone bridge. This way, the real meter bridge is nothing but the exact theoretical Wheatstone bridge. So that's why it's called as the practical form of the Wheatstone bridge. So already we have seen the lower two left and the bottom left and right resistances. They are simply formed by a RAD, RDC. They are nothing but the bottom left and right resistance of the Wheatstone bridge. They are just formed by a single uniform resistance wire whose length is 1 meter. So that way the meter bridge can be really seen to be a practical form of the Wheatstone bridge. So it's very easy to apply. A meter bridge can be very easily applied to find out any unknown resistance. So now the actual, so this is the simple construction and the description of the complete Wheatstone bridge, complete meter bridge apparatus. And theoretically also we have seen that it is almost exactly identical to the Wheatstone bridge. Now what is actual working? What is actual procedure to find out the unknown resistance? Procedure is very simple. Now firstly the key is closed. Once the key is closed, immediately what happens is current starts flowing. The current sent by the battery, just again observe the yellow line. The current sent by the battery will immediately divide into two parts. One part flows into the bridge wire AD, A to D and D to C like that. The other part flows through X and the remaining resistances of the meter bridge. So immediately the galvanometer, some part of the current can flow even through the galvanometer. So immediately the galvanometer will show a deflection. Now firstly what is done is the jockey is actually now already we have seen that when current is flowing. Now the left hand A, so already we have seen that the left hand A of the Wheatstone bridge, because it's directly connected to the positive terminal, it will be at a positive terminal of the battery, it will be at higher potential, and the right hand C is actually directly connected to the negative terminal of the battery. So it will be at negative or lower potential. So this higher potential A we have taken to be at about say 100 volts, and the lower potential T C, for convenience we took it as 0 volts. Actually it should be taken as negative potential. If this is taken plus 100 means this can be taken as minus 100. So but still for convenience to avoid negative numbers we took this as higher potential as 100 and lower potential C as simply 0. Now as current is flowing, now again ignoring the galvanometer. So the best way to understand any question or any doubt is there in the Wheatstone bridge, it's better to ignore the galvanometer. So ignoring the galvanometer, just observe here, again we are coming back here. It's better to follow the original diagram of the Wheatstone bridge here. So when current, ignoring the galvanometer, as current is flowing from A to B and B to C here. So left hand A is at 100 volts potential, right hand C of the circuit ABCD is at 0 volts potential. So as current is flowing this way continuously, potential will gradually in the direction of electric field current flows. So in this direction current is flowing means what is happening? In this direction electric field is actually present. So in the direction of electric field always potentials will decrease. So this 100 means here it will be 90, 80, like that it will be going on. Somewhere here it will be 50, 40, 30, and finally it will become 0. The same thing happens here also through the lower part of ADC also. This is A, this is what? A D, this is the junction D, and this is C. I'll just write the junction D more clearly. So junction D, this is the original theory we have seen, the very important topic, Wheatstone bridge derivation topic, balancing condition derivation we have seen. So as current is flowing through this part, again ignoring the galvanometer. Galvanometer, if it is imagined to be present, means it gives rise to many complications. The reason is current can flow in galvanometer in two ways. If B is at higher potential, it will flow from B to D. If D is at higher potential than B, it will flow from D to B. So that makes it a little complicated in different situations. If galvanometer is ignored, everything becomes simple. Later, we can just imagine that we can put back the galvanometer here and solve the given problem easily. But firstly, ignoring the galvanometer. So as current is flowing from A to D and D to C here, what is happening is in this direction potential is decreasing. So this is 100 volts, this is 0 volts we have taken. So 190, 80 like that will decrease. Somewhere D, at some point D, potential will be 50 volts, the same as B. So then potential at B and D are equal means potential difference between B and D will be 0. So then current in the galvanometer will be 0. Then the current in the galvanometer is 0 means the bridge is said to be balanced. So that is what is balancing condition we have seen. What is the balancing condition for the bridge to be balanced? Current should be 0. If the current is 0 already, what is it? We have seen the relation between PQ, R and S is what? P by Q is equal to R by S. That is what we are using here. So now just observe here. So this is the left hand X. So X is like P. So this is exactly like P. X is like P. So again I'll use a different color. So just see here. I don't want to change the actual diagram. So this is P. So I'm using a pencil. So instead of pencil, actually pencil will not be possible here on the screen. So this Q and this is what? RAD is what? R, and RDC is what? S. So that is very simple. So P and R are actually joined at the left hand A. That is the thing here, ignoring the metal strip A. So P and Q are joined at the point B. Again, ignoring the entire dimensions of the metal strip B, treating it as a point. And RB and S, RB, right hand RB, right hand of RB. RB is nothing but Q here. Right hand of Q and right hand of S are joined at C. That's the thing here. So now, if the jockey is, what is done is now, point B is at definitely. So P left hand, this is the nothing but end A itself. It is about what? 100 volts potential. And Q right hand is at what potential? Its right hand is what? C. It is at 0 volts potential. So the point B is actually between the, this is 100 volts potential. Entire metal strip can be read as point A. Entire metal strip, so entire metal strip M can be read as point A itself. Entire metal strip N can be read as point C itself. So this is left hand of P is what? 100 volts, and right hand of Q is what? 0 volts, because it's nothing but point C itself. So B is in between, some 50 volts. So definitely B has to be lying between this potential, left potential 100 volts, and Right potential of Q is what? 0 volts. It's around 50 we are taking for convenience. But what is the potential of jockey? That depends on the point D. So there is a point D between A and C having the same potential, 50 volts. So if that is same as B exactly, that is, B is at 50 volts potential and D is also 50 volts, then galvanometer will be 0. Current will be there. That means the bridge is balanced. Now what if jockey is pressed directly? Jockey is just a metal strip here. Already we have seen this is the wire. This is a wire going like this from the top end of the jockey. Jockey can be moved. It's not fixed to anything. We can just remove the jockey immediately above the wire and just place it on the wooden board itself. So without forming this contact also. Now just move the jockey here and then firstly press the jockey at the left hand A. Left hand A is at what potential? Already we have seen it is 100 volts. B already we have seen that we took it as around in between 100 and 0, 50. So 100 to 50. That means from A to B current will flow. That means the galvanometer current will flow in the upward direction from A to B if the jockey is pressed at A. Then deflection due to the upward current will be in one direction, the galvanometer will show deflection. What if the jockey is pressed at C? Jockey is pressed at C. C is at what potential? 0. So now the galvanometer top end is at B. It's 50 volts potential. Bottom end jockey is where? 0 volts. So now 50 is greater than 0 here. That means now current will flow from B to jockey when the jockey is pressed here. That means the current will flow to the galvanometer in the downward direction. B into jockey when the jockey is here. When the jockey J was here at A, current is flowing from jockey to B through the galvanometer. Now when the jockey is pressed here at C, current will flow from B to B into the jockey here. That means the downward direction. So galvanometer will show opposite deflection. So this way we can just check whether if all the connections are exactly made like in this. Theoretically, we can say that by pressing the jockey at the left hand and right hand, we'll get opposite deflections. We are getting opposite deflections. This way, we can just test whether all the connections are right or wrong. Now, this is found to be the best way to test whether the connections are right or wrong. So, that way, confirming that the connections are right, correctly made or not, then the actual experiment can be proceeded. So, it's very simple. Experiment is very simple. Firstly, the jockey is pressed at the left hand A. Then immediately current will be flowing. We already seen that A is at a higher potential 100 volts, B is at 50 volts roughly. So immediately galvanometer will show a huge deflection. In one direction it will deflect because a large amount of current will be flowing. Then what is done is slowly the jockey is moved along the bridge wire from A towards the other end. So finally as it is moved like this, what is happening is the deflection will go on decreasing because initially potential difference between A and B is what? 100 minus 50 is 50 volts. Next we'll go to 90 volts. 90 minus 50 is what? 40. So 40. Earlier potential difference between A and B was what? 50. Now potential difference between A means jockey was at A. So potential difference between jockey and B is what? 50 volts. When jockey is somewhere here beyond A at 90 volts potential point, potential difference between jockey and B will be what? 90 minus 50 is 40. Later we'll go to, from 90 we'll go to 70. So 70 minus, when jockey is pressed at the point of 70 volts potential, potential difference between jockey and B will be 70 minus 50 is 20 volts. Like that potential is decreasing. Potential difference across the galvanometer is decreasing as we are moving the jockey away from the point A. So at point A we got a maximum deflection, but as the jockey is gradually moved slowly, step by step, point by point we are moving, the deflection in the galvanometer goes on decreasing, and finally we'll be reaching the point D of exactly the same potential as B. Then what happens? Potential difference will become between jockey. That means jockey is at D, which is having the same potential as B. Then the potential difference between the jockey and B will be 0. The galvanometer will show 0 deflection. So gradually as the jockey is moved from the left hand A, the deflection in the galvanometer is decreasing. And finally, when the point of same potential as B is reached, that point D is called as balancing point, because there the galvanometer current is becoming 0. The bridge is balanced. Wheatstone bridge or meter bridge is said to be balanced. That's why the point D is called as balancing point. Now this is very, very important. Balancing point is very, very important. So I'll just remove the pencil writings, yellow color writings. Even the other yellow lines are also I am removing. So because diagram should be as simple as possible. Any doubt is there, you yourself can draw all these. So during explanation, so whatever I'm just showing here, whatever I'm yellow color ink I have used for understanding. So the same things you can make on your own and you can find out the reason easily. Any question answer can be obtained from the diagram itself. Real experiment need not be done. So always a scientific diagram will be much more convenient to understand compared to the real experiment. Once the scientific diagram is understood, a scientific diagram always is what? A simple line diagram, just simple lines. When you take a real meter bridge photograph, in the photograph is always three-dimensional, it will be looking like, it look like three-dimensional diagram. Many things will not be clear, but in a scientific, a simple line diagram, each and every detail will be clearly visible. Any question is there, instead of performing the real experiment, here itself it can be understood. Certain doubts, really experiment has to be done in certain situations, but most of the situations from the line diagram itself, almost any answer can be obtained. Answer to any question can be really obtained. So now once the balancing point is obtained D, this length AD opposite to the unknown resistance, this length AD, it is less than the total length 1 meter. 1 meter means 100 centimeters. This length AD, which is less than 100 centimeters, is called as balancing length. So I'll just use the same color again, blue. So this balancing length is noted as L centimeters. And the remaining length DC is what? Total length AC is what? 100 centimeters. This is L centimeters. So remaining length will be what? 100 minus L centimeters. That's the thing. This 100 minus. So this L centimeters, this 100 minus L centimeters. So centimeters I don't want to write here. If I write here already diagram is congested. So we're just imagining it to be measured in centimeters. Then only 100 will be coming. Otherwise it will become 1 meter minus L where length is taken in meters. So it's a part of the total length 1 meter means it will become, instead of 40, supposing it's 40 centimeters, it will become 0.4. If we take 100 centimeters as 1 meter, so 1 meter minus 0.4 is 0.6 meters. So decimal points are always complicated. Always it's better to avoid complicated things. So numbers, always better to avoid negative numbers. That's why you're using positive potentials only. Higher potential we took 100 volts, lower potential we took 0. So sometimes they will not be working. Negative numbers will be much more convenient. That's why negative numbers have been invented. They make certain things very easily understandable. Even gravitational potential also, gravitational potential energy also, we have seen that it's a negative number. A regular potential energy, gravitational potential energy, we have seen that it is mgh. mgh. This we have seen almost in the entire mechanics, half of mechanics. We have seen potential energy to be only mgh we have used. But once we reach the lesson gravitation, positive numbers are inconvenient. So gravitational potential energy is defined using negative numbers. There we have seen the gravitational potential energy to be what? Minus capital G, capital M, small m divided by R, or minus capital G, M1, M2 divided by R, where M1 and M2 are the two masses, or capital M and small m are the mass of the earth and mass of the stone. Smaller is the distance between the two masses. There potential energy really had to be taken negative, then only that will be convenient. Derivations will be simple. MGH will not be working. It will create many problems. So the same way here also, as much as possible we are avoiding negative potentials, negative numbers. The same way another complicated thing is decimal fractions are more complicated compared to whole numbers. If you are using centimeters, everything will be whole numbers. That's why we are using length to be in centimeters. So that's the thing. So now this way the balancing length is noted down exactly, which is the length AD opposite to the unknown resistance X. Once that is noted down, remaining length DC will be what? 100 minus L centimeters. So that's the thing. So now with the help of these values, use easily the unknown resistance X can be calculated. Now because the bridge is balanced, the meter bridge is balanced directly, bridge is balanced, automatically we can use the balancing condition. So what is the balancing condition? Very simple. So I'll directly go to the side using the balancing condition of the Wheatstone grid. P by Q is equal to R by S because it's balanced. So what is P here? P is X. So X by P and Q are what here? Top, left and right resistance. This is P, Q, this is R and S. So top, left and right are P and Q. So top left is P is top left, it's X divided by Q is what? Top right. Just check this again here. PQRS. PQRS, best way to remember is PQ is what? Top left and right. R and S is what? Bottom left and right. So P by Q is equal to R by S. So top left by right is equal to bottom left by right, R by S. So top left by right is P by Q is what? X by RB. So very simple. Is equal to bottom left by right. What is the bottom left resistance here? This is R and this is S. R is what here? RAD. Resistance of AD portion divided by bottom left by bottom right. Bottom left RAD we have written and bottom right is what? RDC, that way. But now the important thing is resistance. This is a uniform wire. For any uniform wire, the resistance, we have already seen that previously, is directly proportional to the length of the wire and inversely proportional to the area of cross section. And the resistance of the wire can be written as some proportionality constant. The proportionality constant is called as what? Specific resistance, rho, it's called as L by A. So this can be used here. So resistance of the AD portion, its length we know. So in terms of this length, always resistance can be expressed in terms of the length of the wire and the area of cross section. So this entire wire is of uniform area of cross section. This formula will be very, very helpful. So using this here, substituting using this formula here, X by RB can be written as what? X by RB is equal to resistance of AD portion can be written as what? Specific resistance rho into length divided by area of cross section. Rho into length divided by simply area of cross section. That is what is written here in the top RAD place. The same way RDC. What is the length of DC portion? 100 minus L. So again it can be written as rho into 100 minus L. That's the length of DC portion. 100 minus L. Rho into length 100 minus L divided by area of cross section. That's all. This way it can be written. So whatever things we are seeing here are simple. Nowhere any complication is there. So this rho into 100 minus L by L, just put it in square brackets. The reason is already small brackets is used for covering, enclosing 100 minus L expression here. So now in this, now this is rho L by A. This is rho into 100 minus L by A. What is rho here? It's the specific resistance of the material of the wire. The entire wire, bridge wire AC, is of the same material, same uniform area of cross section also. So area of cross section is same. So both numerator part area of cross section, denominator part area of cross section will get cancelled. The numerator part belongs to first part AD and denominator part actually belongs to second part DC. Both have the same area of cross section, so it can be directly cancelled. This part can be cancelled here. This and this can be directly cancelled here. So next rho is the specific resistance of the left portion as well as right portion, same. So that also will can be cancelled here. So cancelling of rho and area of cross section. What is there here? This numerator part, what is there? Only L is left and denominator part only 100 minus L is left. So left hand side is what is there? X by RB. So next step is very simple. RB can be taken to the right hand side. So X can be obtained as L by 100 minus L multiplied with RB. That will be the final equation for X. Actually there is no place here. So I'll go to the next page. So next page actually only one step will be there in the next page, not much. So already we got, I'll just copy this, copy and paste this step here so that directly it will be visible. So we got this step. So same thing I'm copying and pasting. So this step, in the next step itself, we'll be getting the answer. I'm just copying and pasting it here. This is step we got. So next step we require unknown resistance X. Take RB to the other side. Therefore, X will be how much? L divided by 100 minus L into RB. So substituting the balancing length L here, say whether it's 40 centimeters or 30 centimeters, and substituting the resistance value, known resistance RB of the resistance box used in the resistance box, calculating this, simplifying this, or doing the calculation, we'll be getting the unknown resistance. So that's the formula. So the final equation, the best way to remember the final equation is this only. And this can also be written as this also. Anyway, it can be written. So both are very simple, but this is of almost same form as Wheatstone bridge balancing condition. P by Q is equal to R by S. P by Q is equal to R by S. P and Q are what? X and RB. R by S are what? RAD and RDC we have seen. RAD and RDC. RAD length is, because resistance is proportional to length, only lengths are remaining because the specific resistance rho and area of cross section got cancelled. So in resistance is proportional to length. Resistance by resistance is nothing but length by length we got. Their lengths are getting substituted here. That's what. So this way it's actually much more easier to remember. It's almost looking like the balancing condition P by Q is equal to R by S. So top left by right is equal to bottom left by right. Bottom left by right is, they are proportional to lengths. So only lengths we are putting here. Bottom left and right resistances. Only length, in terms of their lengths we are putting. Their lengths already we have seen that it is L and 100 minus L, that way. So from this we can get this also. I'm just putting this as implies. The above formula implies this. So this is the main formula to by heart it. And this one, if you can by heart this, this was not difficult. Only thing is RB we are shifting. You can by heart this, but this is less important. Once this is remembered, automatically next step we can easily write this one. There is nothing complicated to remember the main equation first step. So using this, substituting the L and RB here. So substituting L and RB here. I'm not writing that because it takes some time. We can easily find out the unknown resistance. So that's the end of the experiment Wheatstone bridge application. So this is the explanation of the application of Wheatstone bridge to the meter bridge. So everything here is very simple, nowhere any complication is there. Now how to write the running notes? Running notes is very simple. So there is not big derivation, there is no big derivation here, just only thing is understanding. So many rough things, rough columns we have used here. This is one rough column. Really see here. This is a rough column we have seen. We have just ignored the complete metal strip M. We treated as a single point like this, and again treating the entire metal strip B as a single point B, and the entire metal strip N as single point C. We have seen that the entire meter bridge is exactly coming like this, exactly coming in this form. So this entire rough column, any doubt is there, this only will be helping. In the meter bridge, any doubt is there, this will be helping. So I'm just keeping this in the rough. Even the other thing also, how the meter bridge is similar to the Wheatstone bridge. Just we have revised everything related to Wheatstone bridge in this rough diagram. So both the rough diagrams will help. This is the real complete diagram of the Wheatstone bridge, and this is the equivalent diagram of the meter bridge. Both are very helpful, but nothing need be written in the exam. In the exam, just a simple explanation will be there, construction will be there, next working will be there, and the derivation or theory will be, it starts from here. In just 2 or 3 steps we are getting the final result. X by RB is equal to L by 100 minus L. This is the final formula which I actually copied and pasted in the next page. From that, even the final step also can be done, but final step is not much important. This final step is not much important actually, because that's previous step is only much more easier to remember. Once that is remembered, this also can be written then and there itself. So this is the completion of the experiment. Now the running notes, how to write the running notes. As usual, in the next frame I'll show the running notes readily written, so to avoid the wastage of time. If I write the running notes, it will take a lot of time. So this is the running notes of the meter bridge experiment. This is really an experiment actually to find out the unknown resistance. So the entire running notes is already, I'm just directly showing the written running notes, so to save time. So entire diagrams, derivation, everything I kept as it is. The only thing is running notes, I've just quickly filled up the running notes between the diagrams and the derivation. So a lot of running notes is coming, but in the exam nothing much will be there. The reason is principle only should be written. So simple principle. Meter bridge works on the, just see here, observe the pointer compulsory, cursor compulsory. Meter bridge works on the Wheatstone bridge principle. What is the Wheatstone bridge principle? Already we have seen in the Wheatstone bridge experiment previous topic. Compulsorily listen to the previous topic Wheatstone bridge. Then the meter bridge becomes very simple. What is the Wheatstone bridge principle? We have seen when the bridge is balanced, P by Q is equal to R by S. That equation can be used. So next, construction. Now construction, most of the construction you just see here, it's just understanding only it's required. Two L-shaped metal strips, M and N, all that entire description you see, it's coming very long. But just see here, now every board exam almost throughout the world, every board exam, the 12th class board or the 11th class board, or even when you go to higher classes, when you go to engineering or PG, that is when you go to either regular BTech or MTech, every essay question actually carries maximum only around 8 marks. That's all. Around 8 marks. Unless it's a very lengthy problem. Very lengthy problems come only in engineering only. Only when you go to BTech and MTech, long lengthy calculations will be there. So there also actually nowadays they carry maximum of around 8 marks or so. So in the 8 marks, so a theoretical question especially in the board exam, but is in the 12th class board exam, main topic actually carries only 5 marks unless it is very lengthy. No, meter bridge carries just in the 8 marks also only 5 marks it carries. So only 5 points. 5 points means one diagram. Diagram is almost equivalent to 2 points. And the derivation, already you have seen the derivation. It is running to about 4 to 5 steps. So that itself will be scoring all the required 5 marks. Then what about the explanation, construction? Now, lengthy explanation already we have seen how it is equivalent to that also. That how the meter bridge is equivalent to the Wheatstone bridge already we have seen in the rough column. So that need not be written again. So even if, without that also, all the description, metal strip M, N, metal strip D, galvanometer G, lucky K, all that it's coming to almost one full page. But this entire thing need not be written. Just see here, this is the starting of the left hand. Only always you have to take the running notes. Firstly, left hand side of the screen. Left hand side of the screen is almost like the board. Left hand side of the board or screen should be taken. Just see, this is a stop one. So just see the vertical bar here, which I am showing with the cursor. Top it is. So then move it to the bottom like this. You can't, it's actually video. You can't move it. I'm just showing it. So you just observe the vertical bar to show to know where the page is ending. So now we are at the bottom of the page. Now again I'm moving the vertical bar up. So again we have come to the top of the page. Now the right hand side is visible. So now again I'm moving it down. So this way any part you can take it down. But the important thing is you take down the entire running nodes. But definitely just see here, from here to here, entire construction, starting from the first paragraph to the last paragraph here, both pages it's coming. Both the left hand side of the page, both halves, both left hand side and right hand side, fully it's taking. But nothing need be written in the exam. You take down this entire thing for the sake of understanding, but just keep it clearly like this in brackets. Just see here, in brackets you are putting and put into means it's not required, actually not required in the exam. Then what should be written in construction? Only 3 lines, last 3 lines actually belong to the next page. I'll just go to the next page quickly. This is the next page. So just see last 3 lines. This is at the first starting of the next page actually. So page 2, you just see here 2, Wheatstone bridge 2. So only the first 3 lines. The meter bridge circuit is equivalent to Wheatstone bridge. Okay, Wheatstone bridge as shown. That's all. Why it is equivalent, all that need not be written. Next, directly working and theory. This is coming to about a half page explanation. This is the explanation. As a bridge is balanced. Balanced means what actually? Balanced means very important thing is because galvanometer current Ig is equal to 0. That is very important. So that also should be mentioned. Now I am mentioning it clearly. As a bridge is balanced, since balancing condition of Wheatstone bridge, what is the balancing condition? When Ig is 0, Pyq is equal to R by S. From that we are getting this step, and next the steps as it is, as we have seen in the explanation. Same thing. The only thing is between the steps, mathematical steps, and the diagram, the running notes have filled it up. So you have to take down the entire running notes quickly. So just once again see the second page. It's starting here. First you have to take the left hand side as it is. Everything should be written in the exam. And next the right hand side. Just it starts here using R proportional L by A, and then the final step here. Substituting L and RB here, X can be determined. That's all. So this is almost the 50th or 51st minute. Both the pages you have to take snapshots and write down the running notes. Quickly write down the running notes and then attend the next topic.